All right, CNT125, Chapter 9. We are in our section on routing protocols, and we just talked about some of these terms right here. On the administrative distance, I'm going to add a little bit more information to that. Here's a chart that kind of gives you an idea of a bunch of the routing protocols. We're gonna touch on each one of these a little bit. When we get to lab, we're going to configure a handful of these so you can get a sampling or a feel for what these different routing protocols are doing. All right, with the administrative distance, I put a bunch of those routing protocols here for you, and I showed you the administrative distance number. Now, as that routing protocol gets used and learns a path, let's say we use OSPF and it learns a path to something, it stamps the 110 number on it for the administrative distance, saying, hey, this is this reliable, as opposed to RIP over here, which would be 120. And the idea is, if we have, RIP learned this pathway or to this network, and OSPF comes along and learns it, the information's better. It would maintain that, as opposed to the 120, because it's better information, if you will. If we have this in the table and a static route's configured to that network, well, then obviously you're going to use this one because the administrative distance is better. Okay, this is also telling us kind of the quality of that information. Keep this in mind. We're going to see these pop up when we start looking at the routing tables. So they now say, okay, there's two different big categories of routing protocols, interior and exterior. Well, interior would be anything kind of inside of our network, inside of an autonomous system. So let's use Hack as an example. Any routing inside of Hack's network would be an interior gateway protocol, some sort of one of these that are here. Okay, distance vector, RIP version 2, link state, OSPF, ISIS, hybrid, EIGRP. These would all be interior protocols to maintain routing paths inside of this company, this network, if you will. As opposed to your edge router and exterior routers would be using an exterior gateway protocol like BGP to maintain the path to these different companies, these different, Penn State, Harrisburg, Temple, blah, blah, blah. All these different types of networks, the routers that are saying, hey, we're going to maintain all the paths to these different companies or these different sites. Okay. So in here, interior, RIP, OSPF, ISIS, EIGRP, in between EGP or BGP. BGP is the main one. BGP is the main one. So let's do a little bit more now. There is distance vector, as we said up here, there was distance vector, link state, and hybrid. Let's get a couple characteristics of each of these out. A distance vector routing protocol would be, examples would be RIP or RIP version 2. They're going to calculate the path, the best path based on distance. Distance and vector tells us direction, if you will. So in other words, how many routers away and in what direction is this network? That's basically it. It's going to calculate best path on distance, how many routers, usually a hop count. Some do factor a little bit more, but it's still usually these number of networks away, these number of routers away until we get to that network. And the idea is if I'm going through 3 routers this way and 9 routers that way, the 3 routers should probably be quicker to get to that destination. They're going to exchange routing updates on, hey, these are the networks I know, and share with their neighbor. Well, this does this on a time trigger, and it's usually broadcast. Time trigger lets you know every so many seconds, every 30 or 60 seconds, they're going to send out an update. And that lets you know it's putting a load on the network, because no matter what, it's going to do that every 30 or 60 seconds, all day long, every day, etc., etc. That is putting a load on the network. The other thing we recognize is if this is a broadcast means it goes to any network it's attached to. And when it hits the next router, the routers typically don't pass broadcasts, so they absorb that information, they turn around and do the same thing. They broadcast it out. That's why they call this routing by rumor. I'm only taking my neighbor's word. I am not talking to anybody else. I'm just talking to my neighbor. So if a network, 9 routers away goes down, it has to pass that along router to router to router to router to router till eventually it gets to me. That's why we have a slow convergence time, and also potential for persistent errors too. During that time that that network 9 routers away, that information gets to me. During that time, I'm still routing to that network over there that's broken. Okay, so slow convergence time. And again, the nickname routing by rumor is a good one to keep in the back of your brain because you're only taking your neighbor's word for it. Link state, OSPF or IS would be examples. Actually, by the way, we're going to configure RIP in our lab first, just so we can see it as kind of like a historical thing. And then we will move on to OSPF, a link state. This focuses less on hop count and more on the state of the connection. And it usually collects information about all the connected links and usually factors them together. And that composite metric is like, okay, we're factoring in distance, we're factoring in bandwidth, blah, blah, blah. This has a higher bandwidth, so we're probably going to get there quicker than going this route over this way. It's going to collect that and build it into its table, and it's going to communicate that information via multicast. Okay, broadcast went to everybody. Routers don't pass broadcast, so it has to literally receive the broadcast, absorb it, and then broadcast it on. The next router absorbs it, broadcasts it on. Absorbs it, broadcasts it on. With a multicast, I can send an update from my router to all the routers essentially at the same time. So I can use a special multicast address that all the routers will read. So my routing update out to the other routers happens much quicker. My convergence time is going to be a lot better. They'll get that information and update their routing table, and essentially they all get it at, I'm using little air quotes here, kind of at the same time. This is going to require, because the router is going to build their own routing table, it's going to require a little more processing on the router. And usually these updates are only sent when a change occurs. So if no changes are occurring, these updates usually aren't sent. It might be really quiet for a long time. So it's not adding that overhead, but it's adding, I do need a lot of router processing to do this. This is scalable for large networks. And last but not least, we have a hybrid category. Hybrid tries to take the best of both worlds. The example we have is the IGRP. That is going to be one of the last routing protocols we configure in the lab, because we're going to look at links. We're going to look at distance vector, then we'll look at link state, and then we'll look at hybrid. This here is trying to capture some of the best characteristics of both. All right, let's take a look at these in a little bit more detail. RIP, again, this is historical. Most places do not use RIP anymore. Distance vector, it only factors hop count. It's going to broadcast the routing table every 30 seconds. That creates a lot of traffic. The convergence time is slow because, again, my broadcast has to go to the neighbor router. They have to absorb it, update their table, and then they broadcast it out to the next neighbor. They have to absorb it into their table, broadcast it out to the next neighbor. So it could take, if I'm saying 30 seconds, let's say it's 3 routers away. Well, 3 times 30, we could essentially be a minute and a half until that router knows that this network is broken or online. Okay, it could be kind of slow, and that's why they talk about convergence time as slow. Because of that, it's pretty much limited to like 15 routers. This is not usable in large networks, and it does not scale well to large networks. There's a limit on that because of that broadcasting the routing table. Here is an example of a network with, here's 2 connected routes, the top and bottom line, and the one in the middle is a RIP route, learned by RIP. So this network is running RIP to update the routing table. So R over here lets us know RIP, 172.16 is the network, 120/1, 120 is administrative distance for RIP, 1 is how many routers away. And I'm going to get there by leaving this port on the router. I jumped out here at the end, I know. Go to this port, go out this port, and then I will go to this IP, and then I will get to this network. Okay, that's what that's telling me. That's how we start reading that routing table. Let's take an OSPF, Open Shortest Path, first. This was introduced as an improvement to RIP. So yeah, you're going to see this a lot more than you would see RIP. This is going to support large networks. It's not using a hop count. It's using a more complex algorithm. It's a cost metric based on bandwidth. The higher the bandwidth of the link, the lower the cost. Again, we're putting little air quotes around that. So if I have high bandwidth links, this number will be low. If I have low bandwidth links or long distances and low bandwidth links, this will be higher. This composite metric will be a higher number. It's going to use link state routing updates, multicast, to pass out any information. And pretty much all major router manufacturers are going to use OSPF or can use OSPF. Here's an example of an OSPF routing table. Again, top and bottom networks are directly connected. This network is learned through OSPF. It's that network 172.16.0.0. I go out this port, fast Ethernet 0.1, to this IP, which would be the IP of the next router. It is a composite metric of 11 away, and there's your 110, there's your administrative distance 110, which is better than RIP, which was 120. So that composite metric lets you know this bandwidth away. You know, if that number were 33, we would know it would either be lower bandwidth or longer distance, or combination of both. ISIS. This is service providers tend to use this one. You might not see this one so much, and familiar is going to be the key. Just recognize what it is. Again, another link state, uses best path, designed for use in core routers. Again, service providers would be the ones typically using this one. So here we see some directly connecteds, and then also we see some ISIS routes there with the I. This network, there's your 115, 10, that actually adds cost of all links. Go out this port to this network, and there I am. EIGRP, this will be one of the last ones we configure in the lab room. This is a hybrid of distance vector link state, fast convergence, low overhead, easier configuring OSPF, yep. Supports large networks. Again, can handle multiple vendors. It was optimized for Cisco, but capable of connecting multiple vendors. And again, it uses another composite metric. Bandwidth, load, delay, reliability, and MTU. The formula combines all these together. And again, the lower bandwidth link will yield a higher metric value. Okay, so I want to see lower values. Lower values mean higher bandwidth links, etc. So here I have, again, a connected route, D is EIGRP. Okay, I didn't make up the code. D is EIGRP. So this network, okay, I'm going to go out this port to this IP, which would be the next router, if you will. There's that composite metric. It's factoring all 5 of those characteristics together. And then there's your administrative distance of 90. You see we're getting better. We went from 120 for RIP, 110 for OSPF. Now we're down to 90 for EIGRP. Last but not least, BGP familiarity. We're not going to configure this one here. This would be, again, something that your service provider would potentially be running. Can span multiple autonomous systems. Most complex of routing protocols, this is basically the protocol of the internet. It uses an autonomous system to identify different networks. So here we have some directly connecteds, and then here's a BGP. This network, I'm going to go out. Here we go. Via this IP, I'm going to get to that network. Okay, so a little bit more complex to deal with. Just recognize what BGP and what role it plays. We'll mention some routing redundancy while we're at this. There is different redundancy techniques, active-active or active-passive. Active-active, it's using both paths all the time. It's distributed. Active-passive, one is set in a backup state and ready, or standby state, I should say. It's on a standby and ready to kick in if needed. But it is key for large companies to have redundant connections to something like your ISP. Different protocols to do this. To do your first hop redundancy protocol can be used to provide a virtual IP, so kind of like a duplicate IP for the 2 different routers to make them look like one to the outside world. Virtual routing redundancy protocol, or hot standby routing protocol, or gateway load balancing protocol. And these all work similarly, that these 2 routers to the outside world look like they're identical. And they're there to basically kick in when the other one is needed. Same thing here with hot standby routing protocol, and then even your gateway load balancing protocol. All right, so these might get used on your edge routers for connections to 1 or 2 or 3 ISP connections for load balancing and redundancy purposes.